Hello, testing, testing. 1, 2, 3, 4, 5. I'll give people a few more minutes to get started. I'm just going to start setting up the solder paste jig. This is going to be my first time assembling a flex rigid panel. You can see I've got the FR4 stiffeners as well as the flex panel, so that'll be a little bit of an experiment and see how it works out. I had to kind of improvise. As you can see, I've got the little piece of FR4 I cut here to stick under the resistors with the intention of hopefully giving me something solid to press against. I couldn't figure out any other way to get paste onto a flexible board that had a rigid stiffener on it. The challenge being that the component area in the tip has a thin, about 200 micron polyamide stiffener, and the area under the SMA connector has a much thicker, about 1.4 millimeter FR4 stiffener, and so the component area is kind of floating in the air, which makes it a little bit of a challenge to get paste onto, so we'll see how well that works. While I'm setting all of this up, I'm also just going to quickly run through a bunch of other camera angles, make sure that they all are visible. Okay, fume hood camera looks to have come loose. I'm going to have to fix that. Stand by. Okay, we had a comment from a viewer about EMI hum and buzz. Is this any better? Okay, yeah, so that was me removing the about 30-foot unshielded audio cable that I was plugged into before. Right now I'm on about a 3-foot cable. If I switch to the benchwork view, you can see right now I've got this mic cable just going from here to the USB sound card. When I have this cable in place, I can't move around the lab. My wireless setup is also pretty noisy. There's a fair bit of EMI around here. So if I'm doing work in the fume hood, you're going to have to choose between that hum or no audio. When I'm sitting at the bench, I'll try and keep the short cable in place. Again, like I said in the original tweets, this is kind of a public beta of my setup. I expect to run into snags, so please, if there are problems with audio or video quality, let me know, and I'll address them before next time. Anyway, continuing down the list of camera angles, just to make sure everything is in place, we got the fume hood view, close-up through the microscope, longer shot of the microscope, benchwork view, VNA, okay, why is that not showing up? There we go. Alright, we got the VNA, we got another angle of the VNA, then we've got the scope screen and the other bay. Perfect. And yeah, right now I'm using a headset microphone. I've gone through quite a few iterations already. The sound quality used to be quite a bit worse. Again, there is a fair bit of EMI from all of the cabling sitting around here. If you look up, all of that Ethernet cable and more elsewhere, and all of the experimental unshielded boards sitting out on benches, I'm actually surprised it's not noisier than it is. I really should put some H-field probes or something on here and just see what my background field strength is here. I'm sure it's significant. But yes, ultimately what I would like is either a proper digital wireless setup that has good noise immunity, or possibly something wired with better shielded cables than I'm using right now, because the current cable, again, it does pick up a lot of noise. Alright, so looks like we've got a couple of people in here. I'm going to start setting up the solder paste stencil, and we'll see how that turns out. There are going to be a few more camera angles added in the future. There's going to be probably some focusing on the test equipment itself. There's probably going to be one looking at the reflow of it eventually. The one in the fume hood itself at the moment is not the best as well, because, let's see if I can just get this to turn. No, that doesn't go down anymore. There we go. I'd like to get a top-down view of the bench here. I would like to get a better one in the fume hood. Right now, the one in there is kind of temporarily secured with double-sided tape. It's also a much older one that only does 720p and not even great video quality at that. Alright, so just trying to get the solder paste stencil lined up. Looks good at that side. Again, this is kind of experimental. I've never done a flex rigid board before, so we're going to see what happens. All of the previous AKL-PT2 prototypes were done... there we go. That looks more like it. All of the previous prototypes were done on Oshpark flex with no stiffeners. They were assembled flat, and then a separate stiffener was just cut out of FR4 and glued onto it after the soldering is done. So this is my first time actually having the stiffener on the board from the fab, so... It's definitely an interesting challenge. The other thing is this is my first time trying to do a large panel board like this. And so I've got all of these tiny 0402 passives and no big capacitors or connectors or anything it can use as an alignment reference. So I might want to put tooling holes or something in this stencil so it's easier to at least get a rough alignment. And I am at the end of my cable here. Interestingly, the PC sound card interface also appears to have EMI issues. I'm using a USB sound card, and I guess having the A to D right next to there definitely helps. At some point, I do have near-field probes. I should go around the lab and figure out just what is making all of the noise, but just to give you an idea of how much cabling is sitting around back there, it could be any one of them or all of them. Alright, looks like the paste stencil is lined up. Yeah, ferrets are a start, but probably not enough. Actually, the AKL-AD1 and PD1, the differential probe, I did some initial bring-up and testing of it fairly recently, and I discovered that the probe tip was the perfect length to be a 2.4 gigahertz full-wave dipole. I forget the exact strength. I want to say it was up to like minus 50 dBm at the amplifier output of Wi-Fi packets showing up on my differential signals. And so, of course, the resulting eye patterns were not that pretty. And so that probe is actually kind of on hold until I solve those EMI problems. I did experiment with putting a ferrite core on the probe. It took about 10 dB off the noise and wasn't nearly enough. Stick-on ferrites didn't do a thing. The common mode rejection of the amplifier is not all that great, and so I may switch to a different amplifier. We'll see. Again, it's active research and development, so. That should be about right. And I need to do the last two now. This is also kind of my test for scaling up to moderate volume production of these. The resistors on the probes are close enough together. I suspect that it would be difficult to CNC place them with a normal pick and place, so they will likely have to be hand assembled at least initially. And so I do want to make sure that that is going to be viable and get an estimate of how long it's going to take so I can figure out what would be a fair price to charge hobbyists. That's not extreme, but at the same time means I'm not losing money on the actual assembly process. So we're going to see. But yeah, these are looking like they're going to have to be hand assembled for now. All right, so this is just a test panel. This isn't the actual boards. I was just trying to verify that everything worked correctly. So I'm going to go drop this under the microscope and see how it looks, and if the print quality was good, then we can go put the stencil back on there and try with an actual panel. You can see, I don't know if you can see in the webcam view, but there's an X on this panel indicating that this is one of the not QA checked ones. It may have some bad boards. It may have just been marked as for testing at the fab, so that's exactly what I'm using it for. Alright, so let's see. Next issue is it looks like the pressure applied by the stick vise is important. It flexes a bit if I am applying force to it, but yeah. Okay, that one's not pretty. That one's a little bit light. Alright. Well, I'm going to have to maybe make a few adjustments, but certainly for today I only need 1 or 2 to work, and so this should be good enough for characterization purposes. Let's just go clean up this test board. I'm probably never going to use this test panel again, but I don't want to get things all sticky. Alright, good enough. Let's open the real thing. So this is the actual pack. This is 4 panels of 10 boards each. They shipped me a couple of different packs that had different numbers of panels in them for some reason. That's nice. There's a little piece of masonite or something to keep them from getting bent in shipping. All right. So it looks like they may have actually had some yield issues on these boards. You can see they've got the marking there on the one about 4th from the top. So that's a defective board, so we're not going to populate that one. I'm actually kind of curious what went wrong with it. Let's hop onto the microscope and see if we can see. It's this one. Interesting. Nothing looks visually wrong with it, but the fab says it's bad, so I'm not going to put parts on it. I probably shouldn't have taken the stencil off when I was done with the test board, but oh well, I can realign it. I really need to find a better solution for this long term. What I'm actually thinking of doing for the next production batch is just getting the boards ordered depanelized already. It'll take a little bit more to set up, but should actually be less work per board, so. At least that's the theory. Alright, that's looking like a solid paste print. Whoops, I was still on the microscope view for that. That will do just fine. Almost ready to start assembly. It is important to clean the stencil right after you've pasted it before you do anything else, because it will get all sticky and goopy if you forget. And I do plan on using this for another 200 some probes in the future, so I gotta make sure everything's nice and clean. Alright, that looks good. Oh, it would help if I turned the sound back on after I put the headset on. Okay, I'll go through the narration again. So this is roughly what the finished probe is going to look like. We've got the SMA connector at this end cast into the block of silicone. I did make some changes to this part of the mold, so this is an early version prototype. You can see the stiffeners showing out of the bottom and so on. So then we've got the silicone potted body, and then at the tip end, we've got, if I can get that focused, at the tip end, we've got the resistors and then the castellations. Again, this is one version back from the final. This is the Oshpark version. It doesn't have the stiffener under the resistors and so on. All right, so let's get to actually assembling. That should be good. So in my experience, it's generally difficult to reflow solder the SMA connectors that I'm using, and actually it's not even possible in this panel layout. You can see that the, let's get that angle right. You can see that the SMA end here actually has stiffener attached to it at the end, so it's going to have to be hand soldered after the panel is put together. For the moment, that's not a concern. We're just going to be reflowing the tip end. Okay, so let's get our resistors. We've got a bunch of little packs of stuff that's half used, so let's see what can I use up. Those are all 50s. The reals are 200 and... okay. Yeah, so these reels are both 200. Let's open up the SMAs. I may or may not use all of them today. I at least want to do two. I want to have one that we can have on the bench for characterization, then one that we can put the silicone on. Although ideally I'd like to characterize the same probe before and after overmolding and see how much of a parameter shift we get from the silicone. My previous experiments have suggested that it's not enough to worry about, but if I do have to make any changes to the impedance as a result of that, I want to know before I assemble 200 of them. The other possibility, of course, is worst case, I can always just sell them as bare boards and not have to worry about overmolding. That would actually make them a little bit easier to make in volume, but we'll see. Alright, so it looks like we've got 5 SMAs available right now, so we can fully populate up to 5 of the 10 that I have here. Okay, so these are all... okay, that's 50s, and these are 200s. Alright, so let's see how many 200 ohms we have. I think that's actually about enough, so... oh, wait, no, these are the 200s. We need 2 of these per board. So, okay, so I will have to tap into the reel. That's what I bought it for. So we've got three resistors on each probe, and that's sticking. We've got 3 resistors on each probe. They're 200, 250 in sequence on the current version. The 200s, we got a question from a viewer. So, Dr. Toon, the first versions that I've got were pure flex. They did not have a stiffener, and so those were just straight flex. This is actually a flexed rigid panel. If I bring up the scrap one again, I'm just going to switch to the bench cam view here. So this is actually a flex rigid with 2 different types of stiffeners. So you can see under the SMA connector, it's an edge lunge connector, and we've got FR4 under the components themselves to provide a nice surface so that the SMA is going to be able to straddle the edge of the board like this. And then also under the resistor, it's a little bit hard to see here, but that darker spot, that is about 0.2 millimeter polyamide, just to give it a little bit of stiffness so that the board won't flex under the resistor and crack the solder joint. And so with this combination, the fab actually asked me if it was okay to put a ring around the whole thing. I guess it makes things easier to handle on their end. All right, so let's just go clean my tweezers once more. I clean my tweezers constantly. Any trace of flux or solder paste is enough to make parts stick to them. Back to the scope view. Alright, so these are the 200s, and we'll see how hard this is to place on a flex board. They do jiggle a little bit. You also notice that placement courtyards are kind of not really a thing on this design. The resistors are placed almost to the point of being in contact, and actually at the extreme of the tolerance band, they would overlap. So I'm kind of playing fast and loose with tolerances here and hoping I don't get two in a row that are both on the big end of the size they're technically allowed to be per spec. The reason being that performance of this design is in no small part limited by the electrical length of the stub between the resistive elements, and what actually matters is the electrical length between the nichrome elements, not between the component bodies. So if I flip one of these over and pop it under the scope just so you can get a better view of what I'm talking about. Let's So you can see that at the left and right sides of the resistor, we've got the gold solder terminals, and then under that green polymer coating is the actual nichrome resistance layer. And so what matters for purposes of reflections and impedance mismatches and so on is the gap between there. So we've already got 300 or 400 microns of terminal at either end, even if the resistor bodies are touching. And what I found as I iterated from the original V1.0, the Kickstarter version, up to what we have now, there was already a significant change in performance from just packing them a little bit closer together. And actually, the AKL-PT1 next version is going to be switching to 0201 resistors. I don't think I'm going to do that on the PT2. The performance is actually right now limited by loss in the flexible material as well, unless I can get a lower loss material. Although, again, that was based on the Oshpark prototype, which was using solder mask instead of cover lay, so it'll be interesting to see how loss on this one compares. So we got 2 on that. We got two on that. And then we're skipping the bad board and on to this one. You also notice that these are flip chip resistors. The resistive element is on the underside. Alright, that's the end of that, so we got to start a new reel. Let's just triple check, verify FCO42, 2000. Yep, these are the 200s. Alright, so we got lots of leader, and where do the parts actually start? The parts, I think, are under there. So if you look, this reel is 100 0402s. It might take me a little while to find them. Alright, so there is definitely some leader, so I think up to about there is blank. I'm pretty sure it's the section under the tape that has the actual components in it. Alright, so we gotta start going slower so I don't peel off more than we need. Okay, I'm not seeing parts yet. Maybe the tape's not where the parts are. Maybe they're further down. Oh, there they are. They're all the way down here. Alright, let's just triple check. We don't have anything on here. The little trash can's actually getting full. I'm just going to go dump that. Okay, so back to finding our resistors. Looks like they start right around there. And how many do we need? We need 1 for the one I'm on, then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alright, let's count out 11 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alright, that was 11 resistors, which is about $20 a parts. Actually, no, more than that. These are like 20, I think like $2.20 a piece or something like that. So I definitely don't want to drop any of them. Let's put some tape on that so I can find the end. That is the started one. This one's a little bit light on the paste. I'm not thrilled about that, but it'll probably be fine. These flip chip resistors don't actually need that much solder. And if I do run into issues, I do test them all, so we're going to see if we see any parameter shifts from that. But honestly, I'm expecting that it's enough, and actually the others I was worried we'd have too much, so. Alright, so that's it for the 200 ohms. Now we can do the 50s. Let's see how many of those we have on. Okay, that's a big one. I feel like I had one that was almost gone somewhere in here. These are 50s as well. I don't know how I ended up with so many different packs of these resistors that have just a few left in them. That might actually be enough. I think that's exactly 8. Is that enough? Or no, I need 9 of them. Okay, so I might need one more. I do kind of wish these were laser marked in the back so you could tell what value they were, but I understand why they didn't. I got paste on the tweezers. Alright, and again, skipping the bad one. Okay, so looks like I do need one more. This one's almost gone, actually. Alright, so visual inspection. Everything is in position. Everything is pretty straight. There is, again, that one I'm a little concerned about insufficient paste, but whatever. I'm making 9 of them. I only need 1 for testing right now. I'm not trying to get production yield. Okay, I think we're ready to go put this in the oven. And now we just turn on the fume extractor and get things going. I don't bother with any kind of a fancy feedback control. This is an unmodified toaster oven from Walmart. I just put it on the cookie setting, set it to 450 Fahrenheit, and then watch the window until the solder melts. So that's what the flashlight is for. It is going to be a couple of minutes while we're waiting for the solder to melt. It's not ready yet, so I'm just going to go grab a few things we're going to need for characterization later on. No, I promise the lab is not CGI. It is real. All right, so boards are out of the oven and cooling. I've got the fume extractor up at max, so we're just waiting for it to suck all the solder smoke and the boards to come down to room temperature. While that is happening, I am actually going to go and calibrate the VNA because I've got nothing else to do in the meantime. Alright, so we've got our calibration kit loaded. We're going from 300 kilohertz to 6 gigahertz, 10K points. And non-insertable. This is one of the things I don't like about Pico's software is if you have this setting wrong, even before you get to the through cal, if it has the setting wrong and you change it at the very end, you have to redo your short open and load calibration as well. So it's annoying. It's a waste of time. It puts more wear on connectors. So I make a point of triple checking that before I start calling. So we've got calibration kit 296 is loaded. And everything looks good. All right. So, port 1 load, port 2 short. Port 1 load. Port 2 short. Confirm load 1, short 2. This is going to take a little while because we're doing 10K points, but for characterization, I always like to do max resolution. Alright, and now we swap them 1 short 2 load. Alright, load on 2, short on 1. Alright, and now we've already got the short on 1, so let's do port 2 open. Short on 1, open on 2. Alright, and then we swap, open on 1 and short on 2. This does take a little while, but Pico doesn't make an ecal, and I'm not sure I'd want to spend that kind of money on something that only goes to 6 gigahertz anyway, so maybe when I get a nicer VNA. I am eyeing one of the Copper Mountain 20 gigahertz ones. It's not going to happen this year, maybe next year, maybe the year after that, but we'll see. A lot of the bigger names like Enritsu and Roden Schwartz don't seem to make small benchtop units, and you can see how cramped this lab is. I really don't have the space for another thing that's, this big across. Alright, 1 open, 2 short. 1 open, 2 short. Alright, so that's done. Now all we have left to do is the through. Whoops, why did I put that away? So this is a known length throw with that CalKit 296. And torque on that, and torque on that. Alright, and Cal should be done. Let's just make sure we got, reference plane extension, everything else is off. We're just going to do a quick sweep and sanity check that we see what we expect. One of the other things that I've noticed with this VNA, I don't know if it's the Pico firmware at fault or if it has to do with the fact that I'm running it in a VMware system because I don't actually have native Windows, and Pico has Linux drivers for their oscilloscopes. They do not have Linux drivers for their VNA, unfortunately. And so one thing that I've noticed is under certain conditions it appears to be correlated with, but not always caused by, using the tone generator feature on the VNA. It will get into a weird state where, as far as I can tell, the receivers are off or something like that, and it just reports full-scale noise on all 4 channels. And so anytime I calibrate, I always finish by just measuring whatever standard I calibrated on last and just make sure I get plausible, sane results. So you can see here, S21, S12 are basically 0, S11, S22 are reasonably low. So that's kind of what we would expect from a through line. So that's an indication that we do have a valid cal and that we weren't just measuring noise. Unfortunately, if you change settings, there's no way to measure without the cal, so I have to go through the whole cal when this happens. When it gets in that bad state, the only solution I found is to just completely power it down and restart it, and it's just a giant pain in the neck, so I don't like it. Alright, so VNA is calibrated. Boards should be cool enough to take out. Let's see how they did. Alright, that one looks a little marginal. We got a lot of solder on that one. But it's probably okay. I mean, we'll measure. Those look okay. That looks good. Those all look okay. Alright, next step is going to be DC resistance measurements. Make sure that these are all good before we start putting connectors on them and depanelizing. We are going to measure again after we've depanelized just in case there's any cracking during that, but again, in-process metrology is always nice. If there are problems, I want to know where they're coming from. So let me go grab some test leads. Alright, and I'm going to use the meter on the right side of the bench over here. It's a Roden Schwartz HMC 8012. I've actually got one on each side of the bench. However, as of right now, the one on the right has a current calibration. The one on the left is overdue, so I always use this one for critical measurements. I'm actually getting a Cal Lab to come out next month to go do a site visit and recalibrate everything. I've got enough gear; it's not cost effective to ship anymore. So once that happens, all this stuff is going to have a current cal. Right now, that meter is out of cal, so I'm not going to use it. All right, so we are on ohms, and I'm actually not going to be able to do this under the microscope. The probes aren't quite long enough. So I'm just going to switch to the bench cam here. And we're just going to do this flat on the bench. All right, so we're going to measure from center contact there to tip. We expect 450, 450.44. Top one's good. 450.64, that's intolerance. 450.44, that one's good. That one's the defective one. I'm just going to measure anyway for kicks. Off scale high, that's to be expected. 450.66. 450.52. All right, this one's reading bad. That is the fourth from the bottom. Do I have a marker around here? All right, I'm going to go grab a marker and just flag that one to need rework. All right, so that is fourth from the bottom. All right, I suspect that was the one that I had flagged as insufficient solder, so I'm going to take a closer look under the microscope when we depanelize. But right now I don't have enough SMAs to populate all these anyway, so I'm just going to not put a connector on that one and worry about rework later. .55. 450.58. 450.49. Okay, all the rest are in spec, so that one is measuring open. So let's see if we can see where it went bad. Oh yeah, you can see it looks like the second resistor on the left side of it. There's just no solder, so I guess that tip side resistor probably reflowed first, sucked up all the solder on the pad. So yeah, it should be easy to fix with hot air and a tiny bit of paste. I will do that. Now is not the time though. I've got enough for characterization. So again, this is initial bring up. Yield is not the focus. All right, I'll keep those leads out here because I'm going to want to measure again after we're fully assembled. Okay, so now I guess the next step is going to be depanelizing these, because if I go back to the microscope again, as you can see, there is no way I can get a connector onto this board as it stands. I got to get these mouse bites off. They are in kind of an inopportune spot. If they had supported only by the sides and left the end open, I could have just put connectors on the whole panel, but as it stands, I have to depanelize. There's no way around it. All right, so let's think what makes the most sense as far as how to do this without further damage to the boards. I guess probably if I break those two and then I flex the ends off, that would make the most sense. So let's see what happens. me just put on some safety glasses just in case something does fly off. Yeah, I actually wonder about for the. I'm not going to bother for these prototypes, but for larger volumes, I do actually have a 2-inch diamond saw. It's basically a table saw with a 2-inch blade, like a angle grinder cutoff wheel on it. That might actually work okay for depanelization. I got it for doing PCB cross section, so I know it can cut FR4. I don't like that. Let me see if I just kind of flex this. Can I get it to snap off? Okay, yeah, that breaks just fine. I don't have to. I didn't want to get glass in my cutters if I could avoid it. I am also getting fingerprint oils all over the Enig, so I'm going to have to clean those probably before I solder them. I didn't think to put gloves on before I did this. Not that it probably matters, but... Alright, so now I guess I'm going to have to scissor cut these off the panel. I can fine-tune cut them later. Right now I'm just trying not to damage the boards. And then let's cut the other end and see if I can just get the whole strip of 10 boards off of here. Alright, so they're all detached at that end. Now I think if I just kind of jiggle this a little bit. Yeah, there we go. They're starting to come off. Yeah, I definitely should get these not on a panel next time, because this is just way too much work. Alright, so that's garbage. The bench now has debris all over it. That's lovely. Alright, so that's 2 boards off the panel. Three. Four. Then we got the bad one I'm not going to bother with, so I'm just going to continue cutting all the way down to here. And there's 2 more. And I missed this one here. Alright, so boards are all separated now. We got a bunch of garbage. We got a bunch of F44 dust in the bench. That's great. Alright, let's see. Let's break off the rest of these mouse bites. This one's good. This one's got one. That one's good. That one's got one. That one's good. That one's got one. That one's got one. And that one's got two. Great. Alright, so I'm just going to go and clean all the dust off this bench. Then I guess I'm going to get the scissors and cut these little tails off here. I'm going to have to sand the FR4 here, and then we can start soldering up a few of these and then start thinking about overmolding. I accidentally hit the volume instead of mute. Let's see. Is this a good sound level? Yeah, it looks good. Alright, so now I am going to go and start cutting the little nubbins off the sides of here. A little bit is okay because it'll be caught in the overmold. It might actually help it stick better, but that much is going to be sticking out of the side and be a weak point, so... yeah, those are probably okay. That's probably fine as is. That I'm going to trim back a bit. Alright, that's probably good except for up at that end. That actually gives a cleaner cut if I do it further down like that. Good to know. Yeah, this is a huge pain in the neck. I can't think of a better way to do this, though. If anybody has ideas, please let me know. I'm sure if I had a CNC fiber laser or something, this would take a few seconds, but I don't. I got so much little capped-on bits all over this bench I'm going to have to wipe up after I'm done. Alright, was one of these the bad one? No, okay, these are all the good ones. This is the bad one, so I'm going to mark this one separately. You can see it's got the little marker dot on that, so this is the one that I think had the bad soldering on it. We're going to take a closer look at this one after I'm done cutting. I am still going to process it just like all the others, though. Just won't put a connector on it today. Alright, getting there. So yeah, let's see what we can see on this one now that we've got a better view. Oh yeah, you can see on this, let me switch to that view. Yeah, you can see very clearly the left side of actually both of the right two resistors, it looks like, are completely dry. So it looks like one side reflowed first, it stole all the solder, and the other side didn't get any. So yeah, just a tiny little dab of paste and a bit of hot air, and this will be fixed, so. All right, 2 more to go. Okay, so that's all of the little polyamide bits removed. Now I gotta deal with all of the rough FR4 edges you can see in the microscope shot here. That'll come off nicely with some sandpaper. I don't want to do that on this bench because it'll make a huge mess. I'm actually going to do that in the fume hood. I like to do all of my messy work in the fume hood, even if it doesn't actually produce vapors, just because it's a nice, contained, easy spot to wipe down and clean up. No electronics around to worry about getting wet or anything. So I'm just going to go clean up this bench and then move these to the hood and get some sandpaper. There will be no audio for that, though, because the either the long cable and lots of background noise, or I use the mic on the webcam in the hood, which is, you're just going to hear wind constantly, so. So to whoever was saying that the lab was super clean, that's why it looks that way. Okay, so that's the sanding complete. Sorry about that. That's the sanding complete, and now I'm just going to go and get a damp paper towel and clean off the FR4 dust off of them, and we should be able to start putting the SMAs on next. I am actually going to do one last thing before I solder any of these. I'm going to go and test fit each of these boards in the overmold just to make sure that they will fit when the time comes to do that. I don't want to have to sand them once I've got the connectors on there. So just a last fit check. So they do all fit, is the good news. The bad news is the fit is super snug. I'm actually going to pop under the microscope for a second and have a look and see. Yeah, so what it looks like is Osh Park had a. Let me see if I have any of the Osh Park probes sitting here for comparison. Okay, yeah, so this is one of the Osh Park probes that were made off substantially the same Gerber. The only change that I made here versus the final version at Miltech is I'm using Coverlay instead of solder mask, and I added vias in this little stretch here. So if you saw my tweets on this a while ago, not having the vias in this area was actually a huge problem. what happened was this bottom ground plane here, you can see it's got a cutout there to match the impedance because the SMA connector center contact is just a little bit fatter than the coplanar waveguide here. And so you can see I pulled the ground back here, but that wasn't enough to bring the impedance back up to 50 ohms. And so I had to add a cutout in the ground plane here. And somehow I didn't detect this, or I might have just never simulated the whole board, because I think at the time I did this. Yeah, okay. I made this version in November, and so, yeah, that was before I had Sonnet Gold, and so I didn't actually have the capacity to do a full board simulation like this. The design size cap was too small, and so I didn't actually simulate the whole thing. And so what ended up happening is this little U-shaped region of ground plane here ended up being a 5.8 gigahertz patch antenna, essentially. And so ground currents in the top side were coupling into there, and it was resonating, and I had about, I think it was like a 5 or 6 dB dip in the response at 5.8 gigahertz. And obviously that was no good. And so I fixed that in simulation. I confirmed in Sonnet Sim that it was fixed. I never made a new board with that fixed. I jumped straight to the production, hopefully, board rev. And so hopefully we're not going to see that 5.8 gigahertz dip in these boards. So that's one of the things that we're looking for in the characterization here. But the other thing you'll notice, if I try to get these two boards to sit side by side here, you can see that the Oshpark board is just a tiny bit smaller, it looks, than the Multec board width-wise as far as tolerances on the edge cuts before the mouse bites and so on go. And so, really, there's two ways that I can deal with this. One of them is to sand down all of these boards by a substantial amount, take off probably 100 microns on either side, which I could do. It would be a giant pain in the neck, and I'd rather not. I'm actually going to take a look at how some of these are. Okay, yeah, so they're this little gap here, you can see with the mouse bites that the copper isn't going quite all the way to the edge here. And it also looks like I sanded the edge here. So that's actually potentially a problem here. We'll see if I get any variation in response here. Again, these are not super high performance probes. Based on loss in the flex, I'm expecting actual 3dB bandwidth of these to be somewhere in the 4 to 5 gigahertz range. And so that small of a mismatch is probably not going to be a big deal. But again, we'll see what happens when we get them on the VNA. We can see here that that's not a lot of overlap, so I may actually put some of these back. Yeah, I think I'm actually going to sand these a little bit more. I'm not thrilled about that. Yeah, I think I'm going to sand the back edge more so that these end up having a better fit to the SMA. I might sand the sides a little bit more too, but I think longer term, just to avoid spending too much time sanding on production ones, I think when I respin the mold, which is going to have to happen anyway for other reasons, I think I'm just going to go and make the mold cavity a little bit larger in this dimension so that we can afford to just put more silicone over here and not have the edge of the FR4 sticking out. That's probably going to be the best route. But yeah, I think what I'm actually going to do is I'm going to pick two of these to assemble fully today, so two that don't have the black marks on them, and then I'll worry about the rest later. So I'm going to put these over here and deal with them later. So we've got two SMAs. We're going to assemble two of them right now. I will sand them a little bit more first. I'm going to characterize both of these as is. Then I'm going to overmold one of them, and then tomorrow I'm going to compare characteristics of the overmolded one to the one that I didn't, and to the overmolded one before I did that. So we're going to see what happens. But yeah, I'm going to go hop in the fume hood and sand these just a little bit more. Okay, that's interesting. My views from the overhead camera seem to be out of sync. Let me see if I can fix that. Alright, well that's something I learned. Apparently when you have OBS set to pause a stream when not visible, it will resume what was buffered, and so it was playing probably a couple of minutes back views from the HUD. Good to know. Like I said, this is why this is a beta. Okay, let's see if these look any better. Alright, we got a lot less mess on that. The SMA fits a lot snugger on that one. That one's not so hot. Yes, that's a problem. I don't have the microscope in the fume HUD, and I don't want to put dusty stuff on the bench here, so I got to keep going back and forth. Alright, I'm going to go and sand this one just a tiny bit more, and I'm actually going to run upstairs and grab some more paper towels for cleaning these up. I'm almost out down here. Alright, so it looks like these are probably both good. No, these are standard paper towels that I'm using. I figure if I'm doing them for the initial rough particle clean after sanding, there's so much debris on there, a little bit of lint isn't going to matter. I am actually going to be using Kim wipes for the next step, which is going to be cleaning right around here, getting any fingerprint oils and everything off of the gold before I solder it. So those leave less lint. They're not clean room grade, but they're fairly good. The other wipes that I use for some purposes are these guys here. These are actually, well, you can see under the microscope better probably. These are actually a knit, I forget what it is, polypropylene, I think. When packaged, they are actually class 100 cleanroom grade. I like them just because they're a little bit more durable than the Kim wipes. I can, be scrubbing around a somewhat sharp edge, and it's not going to tear off, because Kim wipes are non-linting as long as you don't abuse them, but they will still leave residue if you snag it on a screw or a through-hole component lead or something like that, and the woven ones won't do that. The other things that I find that are good for that is the swabs. You can see some of them here. I'll stick one under the scope so you can see. So these are polypropylene microfiber swabs, polypropylene handle. It doesn't actually say what the microfiber element is made of. It's some kind of plastic. These are resistant to every solvent that I use, and more importantly, they don't leave any residue whatsoever. I can scrub in pretty tight spots and rub them against sharp edges of components and stuff like that, and they don't leave residue. So, yeah, it really depends on what I'm doing, but I'll just use standard paper towels if it's for sandpaper work because, again, there's so much debris there. The contribution of the paper towel is negligible. Okay, so we've got one here that looks good. We've got one here that looks good. Yeah, I will definitely have to work on getting that, because that honestly wouldn't surprise me if that positional inaccuracy ends up being one of the major sources of unit-to-unit variation in these probes. I mean, I am going to be doing individual VNA calibrations, at least on the Pro Edition, but still, I don't like things that make tolerances worse, so I'm going to have to go address that. And no, I did not bring my Kapton tape, so I'm going to go get that. And to anybody who was wondering why I had background noise in the beginning of the stream, my mic audio was running through this. So I believe it's a 50-foot cable, so. Alright, that should do nicely. Alright, so let's see how all this works. These connectors are always a little bit of a pain to solder because they fit fairly loosely on the bottom. I actually usually add a little dab of epoxy to hold them in place better when I'm torquing them. You can see if I just slide it on here and let go, it just falls off. And so typically what I have to do is I have to tack solder one side, then once it's roughly in position, then I can tack solder the other half, and then I can go from there. You know, actually, the other thing, I almost wonder if I could just put these in the stick vise on the edge. Let me try that. If the stiffener is robust enough that I could do that. Because that would definitely make it a little bit easier to work with if I had that more solid grip. That actually looks like it could work. Alright, I'm going to try that and see what happens. So the tricky part about these connectors, again, since they don't stay put, I really have to pay attention to where my hands are and what's holding a what, because I need one hand on the soldering iron and one on the connector, and that doesn't leave my hand free to add solder. And that is not tacked. Alright, let's go add just a little bit more flux and try again. I love these connectors for their RF performance, but they are the least fun SMA to solder ever. And of course, I don't want to just go touching it because it's probably hot. Alright, let's... Alright, that looks solid. Get all the extra solder off of there. Alright, and that side's good. As soon as you get the connector tacked down and warm, it's not so bad. There we go. And then we can switch to the extra skinny solder for the center contact. Yeah. Wow, that's really floating up there. That's not good. This is really tilted. I'm not gonna be able to solder that. I gotta reheat this. Alright, well that was a giant pain in the neck, but I think it's good now. Now let's just get some flux in here and get some of that extra solder spread out. Okay, that looks a lot more reasonable. Alright, and then remelt that side. Suck as much of it out here as we can. Not my prettiest soldering job, but it'll do. And then just a smidge of flux in there. And we can do the center contact. And I think I actually have too much on that already. Alright, that's more like it. Alright, let's clean some of that extra flux off of here and then onto the other one. Then we can start testing. I was going to shut off the hot air, but I'm going to leave it on just in case. Deflux as much as we can in that trench. I have no idea what the dielectric constant of flux is, but it's certainly not what I simulated, so I'm going to try and get as much of that out of there as I can. Alright, so there is our first finished, not overmolded probe. Now let's go to the second one and try and make less of a mess of this one. So what I'm actually going to try doing on this is something I did on the AKL-PT2 for some of the tests, which is to just have something to press the connector up against as I'm soldering it. And that, just that little bit of counterbalancing force seemed to make a big difference. So I'm going to see if that helps. At some point I'm probably going to have to build a custom jig for this. I don't really see any way around that. Certainly when I start making these by the 100, that's going to be an issue. And I moved it. Great. Now if I can just get everything to stay put for long enough that I can melt the solder on here. I guess the other thing to see if it might work better is a hemostat. I was worried about this sinking too much heat, but it will give me better control. No matter how many times I do these connectors, they're always a pain in the butt. Oh, come on. I guess I can also try just getting a little bit of tape on there on the other side. I think I've done that once or twice. Alright, I think it's where it needs to be. Now if I can just get this to melt. And it moved. Alright, clean the tip. One, try again. See if I can get it in this way now. Oh, that was easy. I should have done that from the start. Yeah, it looks like it's slightly misaligned. I don't know, maybe 50, 75 microns down of where it should be, but hopefully that's not enough to matter. Alright, and what just happened to that camera? That one's not updating either now. So that is microscope area close up. Alright, well, it's back now. Alright, I definitely still have some kinks to iron out in the video infrastructure. I don't know if I'm hitting USB bandwidth caps or if the camera is buggy or what, but that one stopped updating twice on me now. Alright, and that looks good. Finally. So we can turn off the hot air. And then center pin. Alright, I think that's good. And I don't think it's quite making contact. Need a little bit more. That's more solder than I would have liked, but it'll do. And then let's just clean up that little blob up here. Melt those down. Perfect. And now just retin this. Good enough. Okay, so I think we are done with the actual probe assembly work. Let's get that defluxed, do one last resistance measurement, and then we can go stick them on the test fixture and see about getting some S parameters. Okay, let me go put this away. Okay, so what we're looking for now is good continuity between the ground on the tip and ground on the SMA, and 450 ohms from the signal contact in the tip to the center contact of the SMA. So just going to do basic DC verification on each. So that's our ground, and we're measuring, if I can get it to stay put, 90 milliohms. Okay, that sounds about right. And then on the center contact, 450.47. Okay, that's right where it should be. And then on this one, ground to ground, that's a little higher, 200 milliohms. Interesting. Yeah, interesting. I wonder if we'll see a difference in the S parameters from that. It looks like it's making good contact on both ends. I wonder why it's so high. It'd help if I didn't drop it on the floor. So let's see if we see anything funky on the ground. No, the ground looks fine there. Interesting. I wonder why it's so high resistance. I mean, not that 0.2 ohms is likely to be that big a deal, but I don't like variations I can't explain. And then on the signal contact, 450.57. So yeah, that's right about what we expect. All right, so DC resistance check on both of these passes. Now let's go grab the characterization fixture. And let's see. We're going to do... I'm just going to do measurements across a 50 ohm load for these, I think. I'm not expecting the S11 to be as big a deal. I can do that probably with the fully encapsulated one. Okay, this is a little bit of a mess. As you can tell, let's go back to the microscope view. As you can tell, I've soldered and desoldered quite a few probes from this fixture by this point. But it still works. It's pretty straightforward. I've just got a length of 50 ohm transmission line. I've got a SMA at one end, and I've got a point that I can solder my probe across. And then I've got the same thing here as a endpoint with no termination on it that I can go across as well. So actually, since we want to measure, actually, if we're doing S21 just for initial measurements, I'm not going to bother with reference plane extension, or I can de-embed this. I've got rough S parameters for this length that I've extracted, so I'll just de-embed that. So yeah, I guess I'm gonna, let's see what angle makes more sense to do this. So I can either try and do it like this, or I guess probably something like this would work. And then just tape that to the fixture. So what I want to avoid is I want to avoid having it be coming in. I want to avoid having it be coming in directly on top like this, because if I have it coming in like this, then I risk putting forces in the probe as I connect the VNA here. And so I'm going to try and put it in an angle. So I guess I actually should not have put that Kapton tape away, because I'm about to go grab more of it. Or actually, no, I can use... I almost forgot that I have these custom 3D printed adapters that actually... No, I cannot use them because these are designed to work on the encapsulated probe, so they won't work until it's overmolded. Alright, I guess I do need to go get some tape. Although I could use these double-sided pads. These will work fine. Alright, so we've got the probe stuck down there, and the idea, at least, is that I should be able to come in like that and be pretty close to that 50 ohm load. Alright, yeah, that'll work nicely. So let's stick a bit of flux on here. There's probably enough solder on there. I don't have to add any more. Let's get that off. I may actually have to add solder on that center contact. We'll see. Okay, yeah, I am going to have to add just a little bit. Let's do the ground first. That'll help hold it in place. This fixture is actually also a little bit tricky because it's a coplanar waveguide and we've got so much exposed copper on the underside. I may actually... I'm just going to quickly short check here, make sure we don't have our signal shorted to ground. Okay, yeah, our signal is very close to the ground there. I may actually want to fix that. Alright, are we not touching ground now? Alright, we are not touching ground now. And now let's get just a... tiny little smidge of solder on the tip. Alright, confirm we're still not shorted. We are shorted. Lovely. Oh, wait. Oh, of course, it's measuring 50 ohms because we've got the 50 ohm termination there. So, not shorted, but 50 ohms, and that's exactly what we want to measure. I'm going to do a more exact measurement later, but right now this is good enough. We are not a DC short to ground, which is what we cared about. Alright, so clean all of that flux residue off of there. Go to ohms mode, verify once more. We do not have a 0 ohms to ground. 50.099, 50.1. Alright, yeah. That's exactly what we expect across a 50 ohm load. Alright, perfect. So, we should now be able to actually start doing VNA testing on this. Let me just go grab some tape to keep the leads from moving around. Okay, so my convention for all of my characterization work is the fixture or the tip of the probe is port 1 and the scope end is port 2. So that is port 1. I'm not going to try and torque this right now. We should get good enough measurements without that. And I'm just going to secure the fixture here while we're measuring so we don't have to worry about anything shifting around. Soldering probes are generally pretty fragile at the point of contact. You want to do everything you can to avoid putting stress on that point of connection. obviously when the probes are encapsulated and you've got the little clips holding them in place and everything, it's a lot easier. But right now on the test bench, we don't have that because the board is not encapsulated yet. So. And that is probably going to be good. Let's actually move this a bit. We want it to be more like that. And so now we can tighten that up and not be torquing our connector at all. Okay, that's looking good. Let's see what we get. So again, we're going to start with no de-embedding for now. So we're including the loss of that little bit of transmission line there in our measurements. But this is a good start. And we're going to go to manual and single trigger. And so what we're expecting to see here is a flat minus 20 dB on S21 because we're a 10-to-1 probe. And so we expect to see minus 20 dB on S21, and then on S11 we want it to be pretty flat. All right, we've got a few ripples in S11, and then it's starting to bump up a little bit, but that's not too bad, actually. We're still below minus 10 dB across the termination end probe at 6 gigahertz. We've got some loss here. I'm going to... the Pico S parameter viewer in their VNA software is not great. I'm going to go throw the S2P in Sonnet in a little bit and then pull up a screenshot shortly. So let's save this. And these are, I believe, these are version 0.5, yeah, 0.5C. Alright, before I do anything else, actually, I'm just going to go pull this up, and we're going to see how it looks, and then we're going to see if we need to do any more measurements on this particular unit. So I'm going to run off to, I don't have Sonnet on the lab computer, it's installed on the one in the office, so I'm just going to go take a quick screenshot of that and be right back. Okay, so I've got the data crunched. Let's have a look at it. All right, so to start, here is the S11 plot. It's looking pretty decent. It's fairly well matched out to 4 plus gigahertz, which is the target bandwidth for it anyway. It does get a little bit worse as you get up from 4 to 6, but still, it's not that bad. It's still better than minus 10 dB match, and so for any real system that you're probing this with, I would not expect it to be particularly intrusive. Now, for the fun bit, let's have a look at S21. So, here's our S21 curve. It looks like starting at about 2.25-ish gigahertz, we do start to see some small ripples. I'm not sure if that's an artifact of the current test fixture or the probe itself. Again, I'm still working on getting better de-embeds of the test fixture. Right now, these measurements are with no de-embed of the fixture. Just so keep that in mind. And so what we're seeing right now is that it's pretty flat with a typical low-pass response out to about 4.3 gigahertz. So we did hit the 4 gigahertz bandwidth target. I am pretty happy with this. Let's go see some time domain measurements. All right, I'm going to go grab some supplies, and we're going to go see some time domain pulse response. All right, almost done with setup. Just going to grab an SMA coupler and USB cable, and we should be good to go to start with pulse response, and then we can do some serial data streams and see how that works. Okay, so now VNA's disconnected. Cables are just sitting here. We've got one of Leo Bodnar's, I believe it's a 30 picosecond rise time pulse generator, fed into our test fixture by 3 inches of semi-rigid. Then we've got a 50 ohm termination that we're probing across. We've got our probe coming out here. Then short length of semi-rigid, again, just to keep things from moving around too much during the test. Then a coupler, and then 2 feet of flexible cable going to the scope. So I believe we are good to go. Let's turn off the microscope view there. So, hooking up the signal generator now. And we're in 50 ohm mode. Okay, we're seeing pulses. That's good. Trigger on channel 2. Alright, that looks a little bit more like it. And no, I'm not using Gyroscope Client for this right now. I'm just using the vendor software. We're not doing any fancy analysis or anything, so. So at first glance, it's looking pretty good. We've got nice sharp edges. I'm not seeing much in the way of distortion or anything else. Let's bump our sample rate out. So now we're at 40 gig. Let's zoom in a little bit more. Jump to equivalent time sampling. Whoops. Let's move these out of the way. Alright, that's about as close of a time base as we're going to get on this scope. So this is 200 picoseconds per division. It looks like a pretty smooth rise time. Let's turn on some persistence. Yeah, it's looking pretty good. Let's get some measurements. Okay, I think these are pretty good results. 116 picosecond, 10 to 90% rise time, 79 picosecond, 20 to 80. Keep in mind that this is a 4 gigahertz scope. The datasheet rise time for this scope is 100 picoseconds, 10 to 90, and I believe 75 or 80, 20 to 80. And so this is running up right up against the bandwidth of this scope, which is, again, what we expected from the S parameters, showing about 4.3 gigahertz bandwidth on this probe, and we're using a 4 gigahertz scope. I do actually have a 16 gigahertz scope en route. I have all of the paperwork signed. The dealer powered it on to test it out. It was a refurb. They ran into some problems, sent it into LaCroix, found a bunch of things. A couple parts in the front end have to get replaced. The BIOS battery is dead, and so on. And so I am going to be getting the scope. It's going to be factory refurbed from LaCroix, but it's probably going to be a couple of weeks still. So for those of you who mentioned, or for those of you who saw my tweets previously about the interactive stream on probing technology and so on, that is going to be on hold until the new scope comes in, because it seems kind of silly to do it before the new scope comes in. Anyway, so I think this is about it as far as pulse response. Again, it looks great. I don't have any complaints here whatsoever. And again, the previous version of the probe was pretty decent as is, so I'm not surprised. This is more than good enough that I'd be willing to start making them in volume, which is good because I got 249 more of these that need to be assembled. Alright, so let's turn off our persistence and measurements, go back to real time, zoom way out. Alright, so now that we've got our time to measure. Actually, let me grab a screenshot of what we just had for reference purposes. I forgot to do that. I mean, I could always just replay the stream and screenshot that, but yeah, so let's put that back. I'm just going to grab a screenshot for my own internal use. Oh, and the other thing that I didn't mention also is that this pulse response is after going through, what is this, 6 inches of semi-rigid and 2 feet of flexible cable from the probe to the scope, as well as 3 inches semi-rigid between the signal generator and our fixture, and about 1 inch of lossy ENIG transmission line on the test fixture. And so these are really kind of, I won't say worst case, but they're representative numbers of how the probe would perform in real world use and the actual response that you would see. Ideally, I would like to see de-embedded response of just the probe itself that I can use for, obviously, de-embedding the probe from measurements and so on, and maybe I'll get to some of that later. But before we do anything else, let's do some eye patterns. So for that, we're going to want to turn off all of this and go back to that, add a much bigger time base, and go back to the bench, and I got to do some recabling. So signal generator goes off. And our little 3-inch cable we're done with. So now we're going to get a nice long cable, let's say like a 2-foot one or something like that. And we're going to put a nice little U-bend in there. And run that all the way over to, if I have enough length in this power cable, which I should. All right. And that's going to go over to this, which is a SFP to SMA test fixture, which in this case we're just using as a convenient signal source. I believe right now I've got a 1 gigabit Ethernet link on the other side of these fibers, and so we should be seeing 1.25 gigabit per second 8B10B coming out of this as soon as we hook it up. And so I'm actually going to put the scope back to normal trigger or auto trigger just so I can see what's going on that. Oh, and I didn't change any of the vertical scalings on the scope as well for the previous screenshot. So that was the actual voltage that was coming off the probe. The probe is a nominal 10-to-1 attenuation, and so the voltage on the source is going to be 10 times greater than that. So I am actually now, it's always hard to find space to put the keyboard and mouse when you've got hardware all over the bench. Okay, so back to the scope. So we've got our signal here. I'm going to tell the scope that this is a 10-to-1 probe because it is a 10-to-1 probe. And let me actually move this out of the way as well. All right, so we've got ourselves a 10-to-1 probe now. The scope knows it's a 10-to-1 probe. Let's set our sample rate to 40 gig. And that's a little more reasonable. So we are looking at a differential signal with a single-ended probe, so obviously there's going to be a little bit of EMI and jumping around and so on, and that's just the nature of things. Obviously these are also fairly long cables. There's no shielding anywhere. But let's see what happens if we just pull up an eye here. So we're going to do channel 2 and 1.25 and default PLL. All right, that's not too bad. I like Gelscope clients rendering better, so I'm actually going to pull that up shortly. But this is perfectly serviceable at a gigabit per second, so let's go back to our single grid here and Alright, so here is our geoscope client view. We're going to turn off channel 3, do our default PLL, and that's probably about right. And then I pattern on this using that clock. Make that a little bit more square. We're going to do manual vertical range of, we'll say 200, 250 millivolts. So what you're seeing here as I change, and this is one of the limitations of higher attenuation passive probes, especially with weak signals, is with my particular scope, the front end is only rated for the full 4 gigahertz bandwidth at up to 5 millivolts per division, which is 50 millivolts per division with a 10-to-1 probe. And so if I change the gain anymore, you'll see the signal suddenly turns all rounded, and I don't know if you hear through the headset mic, but there's a little click as the relay switches. And so it's jumping into some mode where it's having more gain, but the performance is a lot worse. Anyway, let's, just to make the eye look a little bit nicer, one of the things we can do is we can de-embed the cable. And so let's do a de-embed on channel 2. Interesting. For some reason, it's not seeing the pop-up dialogues. That's weird. I'm going to have to look into that. But I'm picking out the cable. This is an FL624SM, and I'm just going to pick one of them. And now we can do a clock recovery on that. And if we then specify our data as the de-embed and our clock as the de-embed, now it looks a little bit nicer now that we don't have loss of the cable in there. So the other kind of hack that I'm doing here is that by applying the de-embed, you're converting from the time domain to the frequency domain and back, and this, even if you don't do much for transformation, this acts almost like anti-aliasing on the eye pattern. And so the effect you were seeing before was essentially discretization or quantization noise caused by the front of the scope only having 8 bits of resolution, and we're not even using all 8 bits because of the limited vertical range. And so what we have happening now is since the de-embed is removing the cable loss, but it's also doing a bunch of floating point arithmetic, and so we no longer have exactly 256 unique sample values. Now there's a lot more potential values, and so again, it smooths things out and makes the eye look a lot nicer. And so overall, again, this is it's a wide open eye. It looks perfectly fine for, again, 1.25 gigabits per second on a fully passive probe. That is probably going to end up costing, I don't know, under $100 for sure. I mean, the bare board is about $10. The SMA is about 10. The 3 resistors are $2 each. That's what, $26 or so, plus silicone. And it really depends on how much I can scale up on the assembly and how inexpensively I can. Obviously, you know, I'm working slowly, doing one board at a time, lots of manual stuff right now. So it really depends on how easy it ends up being to scale up to higher volumes. So we'll see. Anyway, I'm going to go grab a screenshot of this. Let's move the de-embed down there so we can see what that looks like. And yeah, there's a little bit of noise elsewhere. It wouldn't surprise me if some of it is Wi-Fi. There is a Wi-Fi access point right over my head here, and you tend to get a lot of 2.4 gigahertz picked up by things. It's difficult to shield just because of how strong it is. Okay, so I guess at this point, question for the viewers. So I've got one board, well, we've got two boards assembled and basic DC continuity checked. We've got this one reasonably fully characterized. We've done S parameters, we've done time domain pulse response, we've done time domain serial data. So now I guess the question is what makes sense to do next. So I can repeat some of these measurements with the second probe we assembled to see how reproducible it is. I can overmold this board, I can overmold the other board. So right now what I'm thinking is probably going to be the best idea is if I were to desolder this board, take it off the test fixture, overmold this exact board, so that way tomorrow I can go throw the overmolded board back on the fixture and compare any parameter shifts before and after overmolding. Does anybody have ideas on any additional experiments or data that they'd like to see off of this board before I pull it off the fixture? Also, if you don't see any activity on the stream for a second, I'm just tweeting a few of these photos. Alright, so we got S21, we got the eye pattern, we've got the pulse response. That should be good. So, seeing no questions from the room, I guess I am going to dismantle this apparatus. I'm going to desolder the board from the fixture, and then we can start with the overmolding process. Alright, so we got that. This comes off. That comes off. I think I'm going to leave the remainder of the cables here so that I can repeat the same setup with, as much as possible, the exact same characterization environment on the overmolded board tomorrow. And obviously, while the overmolded board is curing, we can still do some more experiments on the second board. We haven't touched the second board, really, other than the basic DC resistance measurement checks. So there's still room to potentially do some fun experiments there. All right. So grabbing a bit of desoldering braid, and I'm just going to go take this board off, clean off any flux that could inhibit the curing. I may need some hot air to get this off just because of how much stuff is around here. It's just so much thermal mass. But we'll see. It looks like it may be coming off pretty cleanly, actually. Now my braid is stuck to the board. Well, that's just great. Alright, that was actually easier than I was afraid it would be. Okay, so probe is off the fixture. And okay, probe is off the fixture. No visible damage, everything looking good. Clean off the flux residue and we can start with the overmold. So here is the board that we've been testing with. It's, again, just bare flex PCB at this time, and is obviously some protection is preferable when we're going to be using it as an actual probe, just to make it a little bit harder to break and better insulated, not have to worry about it shorting against things and so on. There is a possibility that I may offer these in a bare form just like this, either for high temperature applications or whatever specialized purposes. However, at least for the time being, I believe that the primary intended final form of these probes is going to be overmolded in silicone rubber. So I'm going to begin setting up for that. So just as an overview again, because the sound quality while I'm working in the hood is not going to be great, even if I will try and get the long wire up. There is going to be some background noise. Bear with me, please. I'm going to try and see if I can get something better to reduce that noise, and maybe even just a second device on that bench that I can use a short cable to and talk directly to and not have to pick up quite so much EMI, or maybe even just pick up like a 10-foot cable instead of a 50-foot cable, so it's less of an antenna. So anyway, what's going to happen is this probe is going to get put into a two-part 3D printed plastic mold. The final volume production is going to be using a CNC'd aluminum mold. That is going to be done after I'm satisfied that the shape of the mold is correct, because CNCing is a lot more expensive than 3D printing. So most likely what's going to happen is I'm going to do one test on this today. Tomorrow morning I'm going to take it out, or tomorrow afternoon I'm going to take it out of the mold. I'm going to see some things I don't like. I'm probably going to make one more revision of the mold. I'm going to 3D print a new version of that mold. I'm going to most likely cast this other board that I haven't yet characterized into the next version of the mold, and if I'm happy with that, then I'm going to order the full CNC'd aluminum mold. That is going to be a gang mold that holds probably 10 boards in it at once, and so that should speed up production capacity a lot, because right now, in addition to the boards themselves being hand assembled, The silicone takes a while. You'll see when we get to that. The silicone takes a while to mix up and prep and everything, and that effort can be shared across multiple boards. But also, it takes close to 24 hours, if I remember correctly, to cure fully. The official cure time, I think, is a little bit shorter than that, but I like to give it longer to make sure it's not going to stick to the mold. And so, what this means is right now, with the current 3D printed mold, my theoretical maximum manufacturing throughput is 1 board per day. And so, obviously, that's not really viable if I'm going to be making these in any kind of quantity. And so the plan is I'm going to do the CNC gang mold, which will let me make a batch of 10 of them, let them all cure overnight, and then make 10 more the next day. And then if I need to ramp up more than that, I can just make multiple copies. Generally, the setup fee for the CNC work is most of the cost. And so I may end up making 2 or 3 of these gang molds, and then I can make 20 or 30 probes a day. And if I end up making that many, it'll be, I'll easily be able to afford to make more molds if that becomes the bottleneck in production capacity. But for the time being, again, this is still kind of final prototyping. These are the very last stages of validation and checking on actual production Gerbers and actual, hopefully, production boards before I start offering these to the general public in assembled form. So backing up a little bit about the actual overmolding process. So the way that's going to work is, first, unfortunately, 3D printed, this is Shapeways, I forget what they call it. I think it's not versatile plastic, it's fine detail plastic, I think. It's a binder jetted acrylic material that's semi-transparent, and the problem is most acrylics are chemically incompatible with platinum cure silicone. So what this means is that if I were to just inject the silicone rubber directly into the mold around the board as it stands, the rubber would not cure fully on the surface. It would be kind of goopy and sticky and gross and attract dust and be uncomfortable to use and less strong, just generally not good. However, obviously 3D printed materials are convenient and easy to work with, especially for prototyping, and I am not going to go custom CNC a aluminum mold for every single iteration of the enclosure design. So it turns out there are surface treatments available that I believe they essentially silanize the surface, and you have all of these silicon atoms hanging off some functional group on the surface of the plastic that binds to the surface of the polymer. And so now the surface of the plastic is now essentially silicon atoms rather than whatever organic groups normally would react with the silicone and inhibit curing. So this works. It's annoying and one more step in the process and takes time, and it has to be redone every time you use the mold, so you're going to see me doing that shortly. So once that's done, I do 2 coats. I let it dry fully. Then I apply a release agent, which is just some sort of, I think it's a hydrocarbon-based oil that sticks to the surface of the mold and prevents the silicone from binding to that, because as it turns out, the first additive, the cure inhibition treatment, actually can act as an adhesion promoter and make the silicone stick to the mold even more. So a release agent is doubly important compared to if I was using something like an aluminum mold. And so once I have that done, then I place the board inside the mold, trying to get as little release agent as possible on the PCB itself, because I want the silicone to stick to the PCB. Then once the board is inserted, I would then close the mold around it, stick it shut. Right now I'm using Kapton tape on the prototype, just a little bit awkward. On the actual production mold, it's going to have screws, so I'll actually be able to bolt the mold shut in a clamshell fashion. Then once that's done, I mix up the silicone and use a syringe and blunt tip 14-gauge needle to inject it through sprues. And it's literally injection molding with a syringe. And you'll actually, I'll try and maybe hold the mold up to the camera while I'm doing this, and you'll be able to actually see the silicone flowing down from the tip end of the mold down towards the SMA connector and then out. So that'll be a sign that we've filled the mold fully and hopefully have a nice bubble-free casting that we can go make the actual probe on. So I'm going to start setting that up. I've got most of the gear in the fume hood ready already. I just got to go grab some clay. So that's another thing that I may still want to fine-tune before I start going into production with these, is where the mold closes right around the SMA connector itself. I need to prevent it from leaking out. And so right now I use a non-oil-based, non-drying, some kind of, I'm not entirely sure what the binding agent in the clay particles is, because it's not water and it's not oil. Um, but whatever it is, it could be some kind of glycol, perhaps. It does kind of smell maybe like a glycol a little bit. Anyway, so I use this clay to seal around the edges of the mold right here, and then I also generally will stick a little bit of it over the tip. And actually, right now, while I've still got the microscope set up, I'm going to go put just a tiny bit of Kapton tape over the top and bottom solder contacts, just to make absolutely sure that, well, I got to go get the Kapton tape again, but just to make absolutely sure that the silicone doesn't stick to the solder contacts to the board. Okay, the end of the probe, as you can see, is now covered in protective Kapton tape. So next step is going to be to prep the mold. I'm going to go unplug the mic and go over there and hopefully be able to narrate while I'm doing that. Alright, so again, my apologies for the background noise. I'm going to try and improve some of the EMI issues before next time, but for the time being, this is what you're going to have to deal with while I'm working over in the hood. So I'm going to go and just put on a lab coat, so if I spill anything, I don't mess up my clothes. This silicone is actually from a film props company. It's completely skin safe, so you'll notice I'm wearing socks, for example, and not shoes. So if I'm working with anything particularly nasty, I'm obviously not going to be wearing socks or open-toed shoes. But if I'm not working with anything where injuring my feet is a concern, I actually prefer to work in the lab in socks because the floor is ESD epoxy, and just natural sweat on the soles of my feet is enough to give me about few hundred K to low single-digit megohms resistance from my hands to ground anywhere on the floor. I have tested this, and so I don't need any special ESD shoes. I don't need to wear a wrist strap. The chair mat is conductive. The floor is grounded, and so pretty much as long as I've got one foot on the floor, ESD is a non-issue. And so if I put on shoes, then I have to start paying a lot more attention to how I'm grounding myself. And so usually I'm only doing that if I'm working with acids or something where there actually is a risk of injuring my feet if I spill something. So if I do spill any of the silicone on my feet, these socks are probably going to have to get thrown out because once the stuff cures, it's impossible to wash out of clothing. But it's not a risk of injuring myself or anything. Anyway, so I'm going to go grab the lab coat and gloves and stuff and set up in the hood. Alright, I'm suited up and the board is ready to go. Let's just double checking I'm not forgetting anything. Once I start working on something, it becomes a pain if my hands are all covered in grease and silicone and stuff, so I try to make sure I've got everything ready in advance. I'm also not thrilled with dangling this cable behind me. It's a tripping hazard, so I definitely need to work on improving that. I really do need to find some sort of a wireless mic setup that works well for this application. So if anybody does have suggestions on something that'll work well for this purpose, please let me know. Okay, so let's see. We've got the board there, the mold. So first step is going to be prepping the mold with the surface treatment. Dropping down into my flammables cabinet here. So we've got our release agent, which we're going to need, and the inhibition function. This is the stuff that we're using. Just pour a little bit of it out into the cup. This is just like a ketchup cup, nothing's fancy. And so the idea here is just that as I'm spraying it across the surface, down the channel, any excess is going to wick down and drip onto there. And we've got a rough layer there, and actually I forgot to grab the Kim wipes, so I'm going to grab a box of those right now. So full coating all surfaces. I don't want any sticky bits stuck on the outside. Even on the outside, residue is a lot easier to remove if it's fully cured, so I do want to make sure I've got a full treatment on everything. And then the inside gets a second pass. For most of this work, the fume hood is complete overkill. Again, it's a convenient spot that I've got available to work in where if I spill anything, it doesn't matter. I've got the drip tray around it and everything. The release agent is some sort of hydrocarbon that does smell a bit. It's, I think, says on the label 40 to 60% VOC. So using that in the hood's probably not a bad idea. The silicone has essentially no smell whatsoever, and so using that in the hood is just purely a matter of convenience again, because I've got it available. This is really the only space I have to do any kind of wet chemical work that's not already allocated for a different kind of work. So it looks like one of the other cameras has stopped updating, so I'm going to go fix that momentarily while this coat is drying. Alright, let's see if that's showing live again. That does not seem to want to update for some reason. Weird. Let's try one more time. Alright, I'm just going to turn off that camera for a bit so it's not cluttering the view, since it's not actually showing you what's happening. Okay, so at this point we've got one coat of the surface treatment on each. Let me just see if there's any questions from the room. Nope. Alright, so we've got one coat of the surface treatment on all of these pieces. It's dried. Now it's time to go do the second coat. And it looks like I need a bit more. And actually that right there was a perfect example of Kim Wipes shedding. So you can see it's still a fairly large piece, but it's got fibers coming off of it. And so what happened is I've got these little pegs on the inside that, these little things that basically notch into the silicone to provide defined flex points for it. And yeah, it snagged on one of those. Okay, so that is our second coat, all good to go. I'm just going to suck up as much as I can of the excess. Rather than disposing of the runoff as waste, I usually just pour it back into the bottle because the only thing it can really be contaminated with is components of the plastic, which is just going to be exposed to again. This is the only thing I ever use this for, is surface treatments of these molds. So I'm not too worried about contaminating the stock bottle. As a general rule, obviously, you wouldn't do that. Alright, so that is done. Now the next step is going to be applying the release agent. Let's just do one last inspection. No debris or anything in there. Nope. Alright, looking good. So this is definitely going to make a mess, so I'm going to put down some paper towels just so I don't get the whole hood covered in hydrocarbons here. So we've got that, and actually what I'm going to do before I put the spray on is I'm going to get some Kapton tape and I'm going to wrap it around the perimeter of each half of the mold. And so the reason for this is that I want the release spray to be on the inside of the mold only. I'm actually going to change gloves after I do this because it gets in your hands. There's no real way to avoid that. And I want to make it so that the outside of the mold is not sticky because I need to be able to use the Kapton tape in order to sandwich the two halves of the mold together and keep them pinched together so that I don't have any leakage coming out of the sides. And so I'm actually going to go put this on. Let's see if I can. This is always a little tricky with gloves on. Sometimes I have to take the gloves off to do this. I don't like doing it because I don't want to get finger oils in the mold once I've put the inhibit stuff on there, but in this case it looks like I'm okay. This is also cheap knockoff tape. It's not name brand Kapton. I made the mistake of buying it on Amazon, and this is what I got. So the glue is not nearly as good as actual name brand Kapton stuff. It peels off very easily. So lesson learned. I won't do it again, but as long as I got the stuff in the lab, I'll keep using it for when I don't really need super strong adhesion. Alright, and that's good. I'm going to leave kind of a tail sticking off the end so that when I'm done, it's easy to peel off. That's the first one done. That is, I believe, that is the top half of the mold. And then this is the bottom half. Same thing, leave some tape sticking off the end. Alright, and that's it for the release spray. Stick these back in the flammable cabinet. I don't like leaving solvents in the hood longer than I need to. And now, try and peel these off. Minimize, again, how much of the surface of the mold I touch with my contaminated gloves that almost certainly are all, I can even feel if they're all greasy. So again, minimize how much of the surface area of the mold I touch with contaminated gloves. Try and drop that out of there. Change gloves. So let's just verify we know which half is which of the mold again. that is the top side. Okay, so I actually have to go put a tiny bit of clay over. Actually, I'm going to try not putting clay over the resistors this time because it was hard to get out. And we're going to see if that gives any problems. So we lay the board into the mold. Let it sit right there. Then grab the other half. Stick that over the top. And there's that. Take all these dirty towels out of there. Probably change gloves again because I was touching the mold again. And this release spray gets everywhere. This is going to be less of an issue when I switch to the aluminum mold because since it's going to have a screw closure, if I get just a little bit of oil residue on the surface of the mold, then it'll still close just fine. So now I've got the two halves of the mold sitting here. Something isn't quite right. They're not... why are these halves not... the board was flexing. That's interesting. Okay, there we go. Hopefully I didn't contaminate my gloves too much from touching the mold. They don't look shiny, so that thumb is a little bit, but hopefully it'll be okay. It'll still stick. So now, right aft of the hull, I don't want to cover the vent hull or the sprue. Stick that around one quick wrap. Then same thing on the other side, just inboard of the vent hull. Tape around the mold. And then finally, all the way around the perimeter, if I can get it to stick. And so the idea here is just to seal the edges of the mold so that we're not going to have any silicone leaking out. We can always trim any mold flash off of the probe later on, but we don't want all of our rubber to escape and leave us with an empty mold cavity. Alright, that is looking good. You can see the, I don't know if it shows up in the camera well, but you can see we've got the little cavity with the mold surrounding the probe. And now next step is going to be to just seal right around the SMA right there with the clay so that we don't have any leakage around there. I'm actually going to have to take the gloves off for this. Dexterity is a little bit limiting on them. So try not to get any of the clay in the threads because we don't want to have to clean those out later. This is another thing I really want to solve before production is this works, it's just slow and labor intensive, and I really want to avoid having steps like this that I have to do for 100 probes. So there is the sealed end of the probe. I think we're good to go and start actually mixing up the rubber. Just washing my hands real quick, getting all the clay off of them so it doesn't stick to my gloves. And again, putting down another paper towel. Obviously, you wouldn't do this if you're working with high temperatures or anything where there's a fire concern, but in this case, nothing is really particularly reactive, and the cured silicone makes a huge mess and is a pain to get off of anything, so I really try to contain any leakage on the paper towel as much as I can. And it also blows around, which is annoying. But hey, at least I know that the hood is working properly. Not that I can't also tell that from the airflow meter, which I think it's off camera, but there is a continuous airflow monitor on the hood, so I know I'm still getting good airflow. Getting that ready for later. This is just a standard 3cc medical or veterinary or whatever syringe. Lure lock fitting. The lock is important. If you get one of the slip tip ones, you probably are going to just pop it off with the pressure needed to injection mold. And then the business end is a, if you can see from the side, it's just a cylindrical blunt tip. It's not sharpened at all. Obviously for safety, I don't want it sharpened. And now we should be good to go and actually start mixing up our silicone. So I think probably for these purposes, let's do like maybe, I think I used like 5 grams each of resin and hardener last time, so let's try that and hopefully that'll be enough. And this is measured by weight, not volume. Alright, and tare it. As you can see, the viscosity of this is fairly high. This is actually low viscosity as silicones go. Most of them are a lot thicker. I spent quite a while searching trying to find one that I'd be able to injection mold easily with hand tools and not needing like fancy powered feed augers and all that stuff to be able to even move it. So we're aiming for about, actually let's do a little less. Let's do 4 grams of each. I think that'll probably be fine. Oh, and I forgot to set up the vacuum chamber. I'll have to do that. To try and keep bubble-free casting, I usually degas the mixed silicone under vacuum. So we're still at 900 milligrams. This might take a while. If I was doing larger quantities, I could just pour it, but with amounts this small, it's difficult. Again, this is one of the things that'll actually be easier about scaling up. Alright, 1900 milligrams, or 1.9 grams. Alright, 2.85, getting there. Alright, 3.73, 3.91, It's bouncing around a little in the airflow. 3.994 grams. We're going to call that close enough to 4 grams. So that's our resin done. And next is going to be the hardener, which is actually a bright blue color. That's where the blue color of the finished rubber comes from. That was not a dye I added to it. I don't know if this is the natural color of the chemical or if it's color-coded so you can tell that you mixed it well or what, but it's actually kind of a nice color, so I didn't bother adding any other colorants to it. The stuff I used before was almost transparent. It was like a milky white color, and I did experiment with different dyes added to it. That was a Shore A8 hardness. This rubber is A25 and is a much more reasonable hardness. A8, it felt like you were trying to, like those sticky aliens in vending machines from the 90s. It was like that. It was just way too soft to actually manipulate it. It almost felt like it was going to stick to your hand, so. And what really threw me off is that hardness of rubber like this, the subjective hardness depends greatly on the thickness of the material. If you have a big solid brick of it, or a small puck, or a very thin coating of it, the thinner it is, the harder it has to be to feel the same hardness to your finger. Because I thought the A8 felt fine when I did like a 1-inch disc of it, and then as soon as I made a probe out of it, it was like, wait a minute, why is it so soft? .3 grams. Again, we're going for 8 total. Did I not get him? .9, 7.95. Alright, it's got to add another 50 milligrams of this stuff. Let's see if I can do that without going over. 7.97. Yeah, depending on the wind, it's reading 8.000, so I'm going to call that good. So these little bamboo, I think they're like hamburger toothpicks or something like that, but they work great as tiny little paddle mixers for stuff at these scales. And then this little dish that I'm mixing the rubber in, this is just like a ketchup cup. Nothing fancy. I buy plenty of expensive lab equipment if I have a good need for it, but I'm not going to spend more on something than I need to if there's a 5-cent alternative. So one of the nice things about this rubber, you can see there's still some swirls in it, so you can tell it's not mixed well. That's something that really helps with this compared to the ones that don't actually have a natural color. Actually, with most of them, I find myself adding a color agent of some sort on my own, not for appearance's sake, but just because when the dye is mixed in well, I assume the resin and hardener are mixed as well. Alright, that's looking like a pretty uniform color now. So now I'm going to go set up the vacuum chamber. which is actually probably going to happen out on this bench here. And actually, it's going to be a little annoying because I've got the Pi here doing the video feed from in the hood. So we're going to see how all that works out. See if I can manage to not shut down the Pi or vibrate the SD card out of it or something. And right now, this pump does not have a switch. It's just a... let me see if I can switch to a different camera angle that might catch this better. Okay, yeah, this looks like it'll show the bench a bit better. So what I'm going to do now is I'm just going to pull a vacuum on the mixed rubber, and we're going to see how well I can get that to degas. Stick a Kim whip in the bottom of the chamber, so if I spill any silicone, it won't make too much of a mess. Alright. Suction valve open, vent valve closed, pressure is at ambient, and let's start sucking. Down to about minus 25 inches of mercury. Alright, it's degassing nicely. I'm actually going to stop the vacuum for a second. Again, I wish I had a camera that could show the chamber, but it was foaming up pretty vigorously from trapped air, and I was actually concerned that it was going to overflow the container. So I stopped pulling vacuum for a second. I'm going to give it a little longer, let all these bubbles pop. And then I'm going to continue vacuuming more. Open the suction valve again. Pull it down as far as I can. Alright, it's been a few seconds without seeing any bubbles, so I'm going to call that good. So, chamber is at vacuum. I'm still seeing a handful of bubbles, but they're disappearing pretty rapidly. So I think we've degassed most of this. Again, tiny little pinhole voids are not a huge concern. I just don't want to avoid like millimeter-sized, multi-millimeter-sized voids in the casting, because that'll mess with dielectric constants. It'll mess with mechanical properties. It can produce a point that it'll start tearing at. There's still a few bubbles rising to the surface. I'll give it a little bit longer. Alright, we're going to call that good. Venting. Okay, chamber is at ambient pressure. And mixed rubber is back in the hood. That's garbage. Put the pump back on the shelf so it's not in my way. And now we can start the actual injection molding process. So for that, we're going to go back to the microscope and fume hood view. And actually the clay can get put away. I'm done with that, and the resin as well. This stuff is a fairly long pot life. I'm not too worried about it. I think it's like 20 plus minutes, so I'm not worried about it setting up on me while I'm tidying up. Okay, so now the mold is ready to go. And I'm going to fill the syringe. One thing that I've discovered is that it is important not to draw the plunger up too rapidly. Don't just pull the plunger all the way to the top and hope for the best. Because what happens is that actually creates too much of a negative pressure inside the syringe. And when the pressure gradient across this lure lock screw fitting is too intense, you will actually start getting atmosphere leaking in around the sides of the needle. No matter how tight you make it, you'll eventually start getting air leaking in. And with a low viscosity, water-based injectable medication, it's not a big deal. Just tip it over and tap out the bubbles. With something a lot more viscous like silicone, that's a big deal. And so I try as much as I can to avoid sucking air into it, especially now that I've vacuum degassed it. There's not really a good way to degas it once it's in the syringe. So nice and slow. You can see I'm keeping the plunger just above the surface of the rubber and pulling just enough vacuum to start sucking it up. Even so, I am still seeing a few air bubbles coming through, so it's not perfect. It's a little bit awkward. Alright, that should be good enough for the first round. I try and fill it in one shot if I can, but I'm probably going to need two. Alright, so I'm going to start filling from the tip end of the mold. So I begin by inserting the needle in through the hull. It slides in pretty snugly, and then just start pressing. And I'm actually going to try and do some of this up in front of the camera so you can see. You can actually see the front of the rubber traveling down. And so once it starts coming out of the vent hull, and that's why I'm putting it down on the bench, I stick my finger over the vent hull. This isn't necessary, but avoiding excessive venting means I waste less rubber, and I'm... Oh, the needle slipped out. And I'm more likely to get the entire thing done in one shot and not have to do multiple shots, which increases the risk of air bubbles. Alright, that's 2 vents. And we're coming out of the third vent. Almost there. And we're coming out of the last one. Alright, so quick little purge, make sure no more bubbles. And we had rubber left in the syringe and rubber left in the jar. So I guess, what is that, 8 grams of total rubber was actually more than we needed for this. So actually, there's quite a bit more. So I guess I'll make less next time, or hopefully be doing a bunch next time. So that's it for that, and this can just sit here overnight. We don't have to do anything to it. I'm just going to move it to the front of the hood here so that it's not going to be blowing the paper towel around too much. So once this cures fully, I can just take a putty knife and just scrape the cured silicone off the top. Obviously, when it's wet, I don't want to try and remove it. Actually, leaving it there helps prevent any contamination or whatever from getting into the mold. So I'm going to leave it like this overnight. Now I'm just going to take the lab coat off and put that away. So I think at this point, that's pretty much a wrap. We've got 2 probes assembled. We've got one of them overmolded and curing. That one's also been fully characterized. This one is just ohm meter tested. So if people want to see more experiments, I can go and set this up on some other devices and try and get some more waveforms off of it. Otherwise, unless there's any questions, I guess we'll close things down for the day. Alright, looking like no questions, so thanks everybody for watching. If you've got any comments or suggestions on either the process or how to improve the lab setup in particular, or improving AV production quality or anything like that, please let me know. If not, I will see you next video, I guess.